right, so now I'm continuing on with the harmonic oscillator. This is video 2 of a 2-part series of harmonic oscillation. So in the last video, I talked about how we needed a wave function that satisfies these specific conditions based on the restrictions of harmonic oscillation, as in we had a potential energy. So now I just gave you the equation of solving or the wave function that's going to satisfy the Schrodinger equation. And now I want to dive into kind of these two components. So we have the polynomial, and then we have the Gaussian. So in your homework thus far, you've played with a lot of exponentials to the minus x squareds. This is why you've been doing this, because the Gaussian functions that dictate harmonic oscillations are very, very common. It's important that you have at least that experience in dealing with those types of functions. So that's why you've been doing that work. So yay, go team, it counted twice. But first, before we get to the Gaussian, I want to zoom in on this one. This is called a Hermite polynomial. So a Hermite polynomial are these very convenient polynomials that have the characteristics that are really important for us. So I'm going to be writing table 8.1. Hang on, the 11th edition, table 7E.1 on the board. So if you want to jump to 7E.1, page 275. Okay, so here are the Hermite polynomials. So if you remember the 3 conditions that we had from before, that the wave function has to fit. Number 1, it has to go to 0 slowly the farther the displacement. The second one, the larger the mass, the faster the decay. And the third one being that as you get wider in the box, you have to, you need a broader wave function. The Hermite polynomials are going to give us that broader wave function. Okay, so for the zero energy state, so if V equals 1, H of Y equals 1, which means, and I'm going to write this psi 1, this little V here designate which energy state that I'm in. So psi 1 is going to equal NV1 times e to the minus y squared over 2. Well, that's not bad. Y2 is going to be, so now the Hermite polynomial is just 2y. So I've got NV times 2y e to the minus y squared over 2. Now let's jump down to the 4. Psi 4 is equal to NV, oh goodness, 16y to the 4th minus 48, hope you can see this, y squared plus 12 e to the minus y squared over 2. Ha. Okay, starting to get trickier. So the beauty of the Hermite polynomials is that they're going to give us these kind of succinct polynomials that we stick in based on which state we're in. Go team. So before, when you were doing the particle in a box, where you had psi of x is equal to square root 2 over L sine n pi x over L, life was groovy. So this is a particle in a box wave function. This is sine n pi x over L. That was your n. The wave function didn't matter. Which wave function fit did not matter what energy state you were in. All of the values were, there's n equals 1, there's n equals 2, there's n equals 3, there's n equals 4, and every time you increased, those wave functions kept those same boundaries. Not the case with harmonic oscillator. So what you get is here, whoops, actually I'm going to pause real quick. Okay, so I redrew figure 7E.6 just so I could clearly show you kind of what I'm talking about how the polynomials or the Hermite polynomials are going to really help us. The conditions that we had for the particle in a box had us, again, you could have any sort of quantum state represented by the same wave function, but it's not the case. And so you have, and we're going to get into quantum tunneling in a little bit, but if the wave function exists, you have, or if there's a slight probability outside of a boundary, that's called quantum tunneling, and it's possible with vibrational motion. And so you have the condition that you have to have the wave function go to 0 quicker, closer to the displacement or the equilibrium position, and then the farther from the equilibrium or the more displacement, it needs to go to zero more slowly. So basically it needs to be wider and occupy a non-zero value up here. Whereas if you compare this first energy state to this 1, 2, 3, 4, 5, fifth energy state, notice how at this point this has already gone to zero, whereas at this point it needs to not be zero on these two sides. Kind of hard to explain that. I really encourage you to look at figure 7E.6 to really see what I'm talking about there. Okay, so this is the Hermite polynomials. We will see something similar to these again. They're not going to be called Hermite polynomials. They're going to be a different type of polynomial called the Legendre polynomials, and those are going to come into play when we're dealing with spherical, basically atom or electrons bound to an atom. The Legendre polynomials are going to give us those kind of globular shapes that yield, after you square them, the atomic orbitals. Okay, so Hermite polynomials, let's talk a little bit more about why they are so badass. So one thing is that they have a recursion relation, which I'm not going to go into much in this video, but the recursion relation is awesome. Okay, so I'm going to erase this and then we're going to talk about how orthogonality can be helpful. Okay, so orthogonality. There is a condition such that the integral from negative infinity to infinity of the Hermite polynomial 1 times Hermite polynomial 2 e to the minus y squared dy is equal to 0 if this Hermite polynomial is different than this Hermite polynomial. So if v prime doesn't equal v, and if v prime does equal v, so if these are the two same Hermite polynomials, so if this is v1 and this is v1, then they're the same, which is awesome, because then what happens is this whole thing equals pi to the 1/2 2v times v factorial, if v prime equals v. You might be asking yourself, why is that so handy, Allison? Well, I will tell you. So in class and in the last video, in a previous video, who cares? I was talking about how orthogonality matters. So if you have wave function 1, wave function 2, dx, if these things are orthogonal, it equals 0. Cool? So if they're orthogonal, that means wave function 1 and wave function 2, there's no overlap whatsoever, that's going to equal 0. That's going to come in really, really handy when we're dealing with molecular orbital theory, where you have wave function overlap. Because if you remember from Stefan's class, if you have orbital overlap, you've got bonding. Kind of. So if we have no overlap whatsoever, we have orthogonality. Okay, and so this is a nice way, if you can get your function into this form, you can be like, oh, I recognize that, that's just 0, because that is Hermite polynomial 1, Hermite polynomial 2 times Gaussian here, and the v prime and the v are not the same, or sorry, yeah, are not the same, so it equals 0. Okay, so you take Hermite polynomial multiplied by the Gaussian, and the Gaussian function, I guess I didn't really talk about that. Looks like that. It's a Gaussian. Cool. Yay. Nice and symmetric. Hooray. And so if you think about for v equals 1, the Hermite polynomial is also equal to 1. So this just becomes a Gaussian. And so that Gaussian function is just the thing that gives it the bumps, or the one big bump. And then when you multiply by the polynomial, that's where you get the multiple bumps stretched out over space. Okay, so if we take this wave function, stick it into h psi equals e psi, then we get energies equals 1/2 plus v h bar omega, where omega equals square root kf over m. Go team. Also, something that's interesting, this right here, this energy, notice how this energy state that I've written as this bar across the picture is not 0. This is 0 right here. So there's actually a little bit of energy already contained in the 0 energy state. So this is V equals 0. So actually, I think I had that backwards on the Hermite polynomials. So when I said that the V equals 1, I actually meant V equals 0 for the Hermite polynomial equaling 1. My bad. Sorry about that. Correction. Okay. The reason I knew that was because vibrational energy states are the only ones that can go, V starts at 0. The quantum number N is going to start N equals 1, 2, 3, and so on. Quantum number J, I believe, also starts at 1. Can it start at 0? I think it can start at 0. L starts at, I think N is the only one that starts at 1. Anyway, V can start at 0. And this 0, if we put 0 in here, E0 is equal to 1/2 plus 0 h bar omega, which is equal to h bar omega over 2. Cool? This is called the 0-point energy. And it's a fundamental energy that exists within the ground state vibrational energy. Cool. Okay, so let's review real quick. So we have 3 things that are originating from this wave function that we've selected for our harmonic oscillator. Number 1 is that the Gaussian, this part right here, gets it to go to 0, makes it go to 0 here. The second part is the polynomial, means that you have at large V values. So this is V equals 1, V equals 2, V equals 3, V equals 4. So at the larger V values, you're going to have it much more broad. That comes from the polynomial. And then the other thing is that, and this is just a direct, well, a direct result from the energy, but you get, since omega is inversely proportional to the mass, the bigger the mass, the smaller the decay. The bigger the mass, the faster the decay, which means a smaller frequency. Okay. I think that's all I want to say. Oh, wait, no, one more thing. So we're going to have a running list of the quantum numbers that we've gotten so far. So we've got the principal quantum number N. And this deals with energy states of well, you've seen N kind of before. In the particle in a box, we're starting to gain information associated with quantum state, or I want to say like the hydrogen atom. But at this point, we still don't have a potential energy that's due to the Coulombic force or the Coulombic potential. And so N is the closest thing we've got to it so far. But this is going to be known as the quantum, or the principal quantum number. We've got V, which is the vibrational quantum number. And so V can equal 0, 1, 2, and so on. N can equal 1, 2, 3, and so on. We're also going to have L, M sub L, and J, where this is the angular momentum. M sub L is the magnetic angular momentum. And then J is the rotational. And then we're going to have M sub S, which is equal to the spin magnetic. And there's also an S, which is the spin. And so we haven't gotten into any of these yet, but I want you to keep in mind that this is where we're going, that the quantum numbers are going to give us, and you learned in 160, actually you learned in 115, that the quantum numbers were really like an address for electrons. That's kind of a lie. They're an address for which wave function satisfies the Schrodinger equation based on the potentials associated with the multi-protons of a particular nucleus. Cool. Anyway, but this is where we're going. So we're looking for the numerical values of these quantum numbers that give us the wave functions that satisfy the Schrodinger equation. Cool. Okay. That's all I got for now.